A single beam transducer sends out a narrow beam of sound pulse. The beam is typically conical or fan-shaped, with defined coverage angle depending on the transducer design and frequency. What it means that the beam angle of a typical single beam echo sounder ranges between 3 degree and 24 degree. Higher frequency transducers, typically 200 and 220 kHz, typically have a narrower beam 3 to 9 degree, while the lower frequency transducers, typically 24 to 35 kHz, tends to have a wider beam. Now here is one interesting fact you might have noticed. As the sonar frequency decreases, it means in the lower frequency, the transducer size increases to keep the same beam angle. So a dual frequency transducer with a lower frequency element tends to be larger and bigger than a single frequency 200 kHz high frequency echo sounder transducer. So which frequency and what beam width is preferable for survey? Well, it all depends on type of survey, depth, resolution requirement and environmental condition. Let's break it down. So high frequency sonar 200 to 300 kHz with a typical beam width of 1 to 9 degree is best suited for shallow water surveys, coastal mapping, harbor surveys, high resolution and precise seabed mapping like detailed bathymetry, object detection, rakes, pipelines, underwater structure. High frequency provides better resolution but has limited or no penetration in deep water. Narrow beam width ensures precise depth measurement. So if you have a sandy or rocky shallow seabed, say around 10 to 30 meter water depth, and if you want to capture the depth undulation of the seabed very accurately, then you should use high frequency single beam echo sounder. Now there is a medium frequency sonar 35 to 100 kHz, very rarely seen, typically has a beam width 8 to 20 degree, is best suited for general hydrographic surveys like riverbed, lakes, coastal areas, navigation safety survey, port and harbor, shipping lanes, and it is good for sediment classification, mud and sand, rock identification. This medium frequency sonar, it balances the resolution and penetration, making it versatile. Wider beam width covers larger area efficiently. So medium frequency is good for areas where there are chances of sedimentation and you want to find out year-on-year deposition, and you also want to have a pretty accurate seabed measurement. And then there is a low frequency sonar which is 10 to 33 kHz, typically a beam width of 10 to 24 degree and best suited for deep ocean surveys, continental shelf and ocean trenches. Sub-bottom profiling. It is good for detecting buried objects and sediment layers. Large-scale bathymetry, mapping vast underwater landscapes. This low frequency, it penetrates deeper but has a lower resolution. Wider beam width allows coverage of large areas. So low frequency is best for deep water ocean surveys that is more than 30 meters of depth. As at a deeper depth, the depth accuracy is not that important. Use low frequency for your dredging survey so that you know how much is the deposition of the soft sediment. Here is a simple table of what frequency is recommended and where. You can pause the video and take a screenshot. If I be honest with you, medium frequency and ultra high frequency single beam echo sounders are very rare and normally they are not used. You will mostly find 200 to 220 kHz high frequency transducer or 24 to 33 kHz and 200 to 220 kHz dual frequency echo sounder. Join this channel as a member to access all the members only videos. So it is always wise to carry a dual frequency transducer for your general navigation survey or general bathymetric survey. Operating both the frequencies together will give you both the higher resolution data and also the sediment layers, and if there is any rock or pipeline buried under that sediment layers. Dual frequency is also better for dredging surveys for clear estimation of volume. For a relatively flat bottom, the first echo will always be at the nadir or directly below the transducer. This may not be the same if you are surveying in a sloped seabed, as the outer edges of the beam may have a shorter slant range and have a stronger reflection back. In this case, the depth is underestimated, or the depth is lower, and it has a potential error increasing as the depth increases, because as the depth increases, the ensonified area increases. Similarly, while surveying close to a vertical structure like a jetty or a platform structure, the outer perimeter of the transmitted beam ensonifies the vertical structure and thus returning with the erroneous depth. So in this kind of cases where we have to survey near a vertical structure or a slanted seabed, we must use the higher frequency and the narrower beam transducer. If you are doing a thalloic survey on a river or a channel from bank to bank, then if you are using a lower frequency wider beam echo sounder, you can have a bigger error in depth as well as in position. I have a video describing details of that, and you can find the link to that video in the description below. So, how do we calculate the ensonified area on a seabed? So the simple calculation is the ensonified area diameter is equal to 2 multiplied by depth multiplied by tan theta by 2. Let's break it down. A single beam echo sounder sends out a conical beam. The beam width is defined by the total angle theta measured at the transducer. Since the beam spreads outwards, half of this angle or theta by 2 or radius is used in the calculation. At a depth d, the beam hits the seabed, creating a circular footprint. The radius r of this footprint can be found using radius is equal to depth multiplied by tan theta by 2. Since the footprint is circular, the diameter of the ensonified area is 2r. So 2 multiplied by depth multiplied by tan theta by 2. Now let's talk about multibeam system.